things that get trapped in the metal as it's carried through the mould and freezes. Indigenous inclusions, which mostly result from the deoxidation process in the ladle, and hidden microscopic inclusions. You don't really know you've had them until something breaks. These are things like type 2 sulfide inclusions, or more insidiously, aluminium nitride inclusions, which are a real thump in the ear. Right, in terms of gases, first one off the rank is oxygen. We can deal with that pretty easily because in our deoxidation process, we're killing it. We're getting rid of the oxygen. And there have been oodles of papers written about the deoxidation process, ladle deoxidation additions, and I think there's far too many for comfort, actually. So I won't add to the confusion. All I will say is that for making carbon low alloy steels, your basic deoxidation for ladles is 1 kilo of aluminium per tonne of steel made, and 1 kilo of calcium silicide per tonne. The calcium silicide doesn't do much in terms of deoxidation because the calcium evaporates very quickly and doesn't get much deoxidation done. But it does give slightly better fluidity, and it does improve the tensile elongation and ductility in test bars. Now, so that's all you really need to know in terms of coping with oxygen. The next one is hydrogen. There's hardly many problems with hydrogen in steel castings unless there's gross hydrogen porosity. And you know where that came from and you know what to do to avoid it. The problems don't really exist in castings because the gas can distribute itself through the micropores and micro shrinkage and thus reduce any pressure build-up. So it's not like hydrogen flaking in forgings where the metal is compressed and the hydrogen gets squeezed to the point where it has to crack. That's not a problem with hydrogen in steel castings. All you need to do is limit your return scrap in charges, because one of the tricks of steel making is to melt oxidizing. One of the main reasons for that is the solubility of hydrogen and nitrogen in molten steel is inversely proportional to the concentration of oxygen. So if you're not oxidizing, hydrogen and nitrogen have difficulty getting into the molten metal. So you can protect from that by
it's dropped out. Hang on.
Fluid steel.
One sec. Can you see Dad and hear Dad at all?
Can you hear me?
You can't hear him?
Absolutely, we can hear you.
Oh.
Yeah.
There you go.
What was that question? Can we?
No, I can only see like all the little circles at the bottom.
As far as I'm concerned, we can hear you. The slides just weren't moving forward.
Yeah, I haven't been told to move slides yet, so.
Okay, so no, that's okay. Not a problem. Not a problem.
Okay.
Dad's, we're just holding on. So you can't hear him at the moment. Is that the problem, or you just can't see him?
No, I
I can't see them.
Jim hasn't asked me to move a slide forward yet.
Oh,
I've been
bugger.
hearing Jim okay.
Okay. Hmm.
You can hear me okay, Murray?
Yes, I can hear you okay.
He just asked if you could hear him okay.
Right, okay, yeah.
Do you want the slides moved?
Yes, you can. No, leave number 1 up, please.
Okay. You let me know when, you tell me when you want a slide changed.
Okay.
Yeah.
Hasn't got into the slides yet. All right.
Okay. Where's it all gone?
Okay, just hang on, Dad. Hang on.
No.
Wait, Dad. Dad, wait. Hang on, we can go like that. Okay.
What are we doing?
They're just waiting. We're just waiting because they don't have you.
No. Murray had me.
Okay.
We can all hear you very well.
Oh, good.
Yeah, we do.
Okay.
Yeah.
Well, shall I pedal on?
So that.
We probably just need to have confirmation if WA can hear us. But Alan Cook speaking. Jim, I can hear you and I can see your slides. Everything's fine.
All right. Well, let's press on because we don't want to run too close to the wind with the timing. If you look at that first slide, it's got nothing to do with the good-looking gentleman wearing a face shield, but look at the shape of that furnace spout. You'll notice it's near vertical walls and its depth, and that's near perfect. When that furnace is tapped, that metal will come out as an almost cylindrical thick wire of steel, which reduces reoxidation from the atmosphere and gets it into the ladle quickly, so you don't have very much temperature loss. Right, number 2, Murray, thank you.
All right.
So what these are the topics we're talking about, but I don't really need to go over them. There are a couple of things here that in the second paragraph I mentioned simple but effective control tools, spreadsheeting software, and one of the most important of those is a spreadsheet or some form of rapid calculation for the liquidus temperature of whatever grade of steel we're making. Right, number 3, slide, Murray.
You don't.
I mentioned in the written paper my preferred my preference for furnace for foundry equipment when you get into the good stuff. There's been lots of proposals for
All right.
getting.
Just stop for a sec. All right. All right, we can't hear you, John. Sorry. Okay, excellent. All right, great. Thanks very much, Chris. Bye. All right, they're back. Okay, so we're going to. That one. All right. Okay, Dave, you can go ahead and just give them a quick summary of what you've done in the last 5 minutes.
Okay, well, in the typed presentation, I detail my preferred list of equipment, and in it I mention spectrometer samples. There's been lots of proposals by people who make spectrometers for casting the thick tubes and then cutting them off and limishing the surface on horizontal discs. But my preference, and it has worked wonderfully well for us, is a simple double-ended copper block, pure copper block. You get it from the metal suppliers, about 4.5 or 5 inch diameter, about the same long. And we simply machine 2 grooves, top and bottom, so that if it got any damage, and you can see from the top right, they do get a bit weathered, you could just remachine it, cut it out, and kick off again. Above that is the simple shell core, which formed the closure, the cope of the mould, the copper block being the bottom or the drag half, to form the spectro sample up in the top left-hand corner. And the bottom face of that spectro sample is the one that we lineaged. It would be just on a horizontal belt, and we used cubic zirconia, I think it was, with the belt, because you can't use a high alumina belt, certainly not when you're analysing for aluminium in the steel. So also among the preferred list of equipment was a ripper of a ladle heater. Lazy flames just don't do the job. What you need is very powerful heaters that can bring your ladles up to 1,000, 1,100 degrees C and hold them there for a good half an hour, because most of your ladle linings these days are aluminium, high alumina. And high alumina is highly thermally conductive. So if you don't heat them up properly, then that heat will seep away to the outside and your metal will cool too quickly and start trapping inclusions that you want to float out up into the slag layer. So they're two of the major features of preferred equipment, apart, of course, from the ladles with the porous plugs, argon stirring, and all the good bits described there. Now, slide 4.
Okay.
We want to make steel. What do we have to do? We've got to exclude all the ugly stuff that contaminates it. And what then makes dirty steel? As I said, four major problems: exogenous inclusions, indigenous inclusions, gases, and microscopic defects. I can rest the slides now, but the most in the gases, I've already spoken to those about your deoxidation. If you have to go to a higher strength martensitic quenched tempered alloy, what were they? The can't remember them now. All with tensile exceeding 650 megapascals. That's in danger territory for aluminium nitride. So we cut back the aluminium addition in the ladle to 0.8 kilos of Ali per tonne, still with the calcium silicide, and for good measure, a ferrotitanium addition to get about 0.025, 0.035 titanium, and that has a very high affinity for nitrogen and will mop up any free nitrogen floating around in the steel. And the problem is it makes slightly dirtier steel, but it's not disadvantageous. The titanium nitrides are tiny little cubic crystals, bright orange if you look at them in the microscope, and they never do any real harm. Hydrogen we've spoken about. One thing to watch for is high humidity. Brisbane, Townsville and up. High humidity used to be a real problem for Bradkin when they had a foundry in Port Hedland, because they didn't realise at the time, but it's awfully hard to make good steel with no hydrogen if you've got a 90% humidity or 95% sometimes. So just keep your eye out. I've often heard foundries say, "Oh, we were doing all right, and suddenly everything went wrong, but we haven't changed anything." They didn't need to change anything. Mother Nature made the changes for them, brought in nasty weather. So hydrogen can be coped with. Limit your foundry returns in your charges, because they are returning silicon and manganese, both deoxidants, into your charge. They're reducing the oxygen in your charge, and the lower the oxygen is, the more hydrogen can be absorbed. And finally, nitrogen. Now, nitrogen can be a silent assassin. And you really have to know how to handle it. Once you do, it's never a problem. I remember going to a foundry in the early 80s, and they were making a new product. So to be safe, they had cast plenty of test bars, luckily. But the first set of bars failed their tensile tests. So they machined another set, and that failed. That set failed. So then they reheat treated the casting and the test bars and tried again, and they failed. 2 sets failed. And luckily by then I arrived on the scene, and they told me what was happening. So I said, bring me the test bar stubs. As soon as I saw the fracture surfaces, I knew what their problem was. It was aluminium nitride. Nitrogen has a nasty effect. As I say, it's a silent assassin. Now make sure you avoid high nitrogen furane sands. Take care in your choice of scrap. Don't try and be too economical. If you use duplex stainless steels in your scrap to recover the alloys, which is a pretty good trick, but you've got to remember that all duplex stainless steels contain not added nitrogen. So that just adds to the nitrogen load in your metal. And the long distance shot, don't get any scrap at all from a heat treatment shop, particularly failed nitrided knives and things like that. You don't want that nitrogen in there either. You can control, after all that, you can control nitrogen then pretty much as I've described up in the handling oxygen. Now for the inclusions. Now, exogenous inclusions are mostly caused by carelessness, untidy or bad housekeeping. Loose sand trapped in the metal is the major fault. Poorly maintained furnace spout, where you have bits peeling off, crumbling off, and getting carried over in the tapping stream. Remember that spout on the very first slide. The strange one that we discovered, that Foundry was making large locomotive bogies, or the 6-wheeler bogies and other cast bogies. And of course, bogies are virtually impossible to make other than by the full core assembly. And when you assemble all those cores together, there are a hell of a lot of core faces rub against each other. And there are particles of sand come off. And when the casting is poured, you have all of the core atmosphere displaced by the molten metal. And there are some extremely violent winds travel through the mould and carry these little odd bits of sand Only took 2 or 3 grains here or there, but they all get carried through into the metal stream and leave you with some awfully dirty steel. To escape that problem, and it was just mind-blowing, the effect, we gave all of our core prints a single coat of mold paint, just to bind the top surface together, and the effect was totally dramatic. And the dressing hours came down by something like 90%. So be careful, particularly if you have to rub cores to make them fit. Make sure you paint the core prints. Train your staff to avoid carrying moulds and whatever over open moulds. Also teach them, whoever's adding the feeding compound, how to do it the right amount and at the right time. The next cab off the rank is microscopic inclusions. Is Indigenous inclusions. And they're mostly from the ladle deoxidation byproduct. So allow time for them to float up in your bath. And that's why back in the equipment recommendation was the ladle burners. And that's why ladle very, very hot, so that your heat loss rate is minimised. It gives the Indigenous inclusions that little bit longer time to float to the surface. Now, also in there was the mention of the spectrometer. You need a good one to analyse for aluminium. You need accurate control of your aluminium deoxidation. So you can repeat it time after time after time and keep that final aluminium to around about 0.04, 0.05. That's the safest sort of level. 0.06, you start running into the aluminium nitride that we spoke of earlier. Microscopic inclusions are mostly intergranular on the original grains, on the original, not the prior austenite grains that are precipitated from normalising or annealing, but the original as cast austenitic grains. And they come at you from 2 directions. One is type 2 sulfides, which is at the bottom of that list. And they cause mostly, in Australia, we hardly ever see a problem these days because the recirculating scrap lead in Australia it is slowly reduced sulphur contents, and there's not a lot of sulphur floating around. But when you do get it, you've got to make sure your deoxidation process is good, because if you get that wrong, you won't get type 1 or type 3 aluminium iron sulfides. You'll get type 2 sulfides, which are precipitated along the grain boundaries and are a real weak spot. Right, slide 5. And that's what they look like. They're mostly a dove grey colour. And that's only about 400 magnification, that slide. But you can see the linear nature of them lying right along the grain boundary. And your tensile strength and ductility go out the window. Then, and finally, the nasty one. Aluminium nitride comes about when there's a combination of factors in steel making or in steel casting. It's a combination of thick sections which relate to or cause slow cooling rates. And when the section thickness is big enough to get a slow cooling rate down in the order of 30 to 50 degrees centigrade per hour, then you have created the perfect wind for aluminium nitride to start precipitating. It is helped by high aluminium and or high nitrogen, but at that very, very slow cooling rate, that's when you've got to watch out. That's why I mentioned earlier in the high tensile steels, we'd use a bit of titanium to sop up any nitrogen, and you do the same with very slow cooling sections. When in an earlier life I was a company was making armour plate, cast armour plate, we always had to be careful because they were very high tensile steels and of course thick sections, and it was drilled into us the proper deoxidation and ferrotitanium addition to avoid it. I think there have been a few papers about ferrosilicon, zirconium, and other deoxidation or other alloys, but I think it was Society, one of the mentioned in the references. He had demonstrated that zircon had absolutely no effect in reducing nitrogen. So forget it. Just stick with ferrotitanium, and you'll be safe as banks. Right. I run out of puff. Now, aluminium nitride. It would be absolutely devastating if you were a member of a tank crew and the steel makers who made the tank turret and armour plate hadn't done the job properly. And your turret suddenly exploded, not through the force of the explosive, but it just cracked, fell apart. In 1945, the American government decided to send expert teams in just about every discipline you could think of over to Europe to gather as much information as they could on what was happening over there in steel making and knitting, I suppose, as well. But in steel making, they noted that some of the steel had been made by the Troponus converter system, which is now well outdated, but it literally blew air onto cast iron and scrap and melted it down. It was a bulk steel making, and it suited steel mills well for speed. But of course, being airborne, what did we say earlier about keeping nitrogen and air away from your steel? Well, blowing it across your steel, you've got quite a bit of nitrogen pickup in converter blown steels. And they proved to be one of the main problems, as we'll see what happened after the Americans brought their specialist teams back from Europe. One of them was Foundry specialists, led by the original Mr. Briggs, I can't remember now, Howard something Briggs. But anyway, they did note that there were quite a lot of cracked equipment, the armour equipment, and particularly in a place called Kursk. Kursk is in Russia, and it formed part of the Eastern Front that Germany was fighting with Russia. A battle of monumental proportions. Some 7,000 tanks and armoured vehicles and 2 million men battled it out there. Russia finally won, but that was because they could replace their tanks and the people faster than the Germans could, who were starting to run out of raw materials. But the damage left all over that battlefield was an eye-opener for the Foundry specialists. All this cast armour and cast turrets. We'll chop some bits out of those and send them back to the States and get unis and whatever to have a look at them to see what caused the problem. And that was duly what happened. And in 1947, two brilliant metallurgists out of Battelle Memorial Institute came up with their solution. They had discovered that the problem was aluminium nitride, which knocked the living daylights out of the impact strength of the armour. And in following years, other metallurgists investigated and developed more reasons, and they came up with the higher nitrogen contents the slower cooling rates and higher aluminium contents. That's why quite a few high-strength alloys specifications limit aluminium now to 0.06 max. I think really it should be a lot lower. But anyway, that's my opinion. I'm only an ex-steel maker. Well, a steel maker, but retired. So, slide 6 now, please, Kev. I think I've covered most of that now. Yeah, 1943 was the battle. And the Americans were particularly interested in what was happening there because they wanted to learn everything they could and find out what Germany and Russia had been doing in terms of science and technology, including, of course, rocketry and ICBMs. But we're only interested in the Foundry bits. But the USA had used castings as well. And so they wanted to know how much at risk their tanks were in the battlefield. And in the next slide, given the Lorigan-Elsie and Woodfine and Quarrel and others, and they defined those as factors. Later investigations have found that those parameters could only be used as guidelines because other complex combinations of factors play a part. But if you, get those factors under control, you've gone a long way to getting aluminium nitride problems beaten. Now on the left-hand side is a Panzer Turret. You can see on the left the huge crack running from the top down the side, a piece, what looks like probably about 60 mil, 70 mil thick armour plate has fallen off. Somebody very politely put it back for the inspectors to look at. A bit missing out of the bottom right-hand corner. And on the right-hand side, the rather ugly fracture faces that you get in those sorts of things, which are very typical of aluminium nitrides. The round bits, can we point there?
No.
No. Right. The rounded bits there are the sides of one grain slowly growing, and the grain boundary was totally covered with aluminium nitride. So I hope that's given you some insight into how other steel makers think and what best practices they employ. There is a lot more in the printed version of the paper. Just because of time constraints, we couldn't go through it all. But not all of these will be directly transferable to your plant exactly as they've been described, but they have worked very well. And there are a number of unstated subsidiary factors, not least of which was an experienced supporting staff dedicated to being the best in the business, and which is what they became. They all contributed to successful practices and outcomes. Without all of those factors working together, you may not experience the same total positive results. Not initially anyway. Finally, work hard at increasing your database of theoretical knowledge and practical experience. Add your own references to those shown in the following references list, and look for more. There's plenty available in the literature. It might seem like fun gaming of a night, but gee, if it was me, I'd be looking for some of these references. Now, I haven't talked about manganese steel. It's a pretty simple one, just the aluminium. And the aluminium doesn't do any grain refining. All it does is stop grain growth. There's a difference. And you don't need much deoxidation of aluminium, manganese steel, because the high carbon and the high manganese just about do all the deoxidation for you. So the aluminium is really only added to prevent grain growth during heat treatment. Now, there are a couple of slight modifications to the basic brew. There's 2% chrome, which is added to limit the expansion caused by pounding hard surface of life, and a couple of moly treated ones, which are more specialised applications. But I had the luck of working for a while in the States with a brilliant research metallurgist, a guy called Howard Avery, or Howard S. Avery as the Yanks address people. And Howard was absolutely astounding man. Apart from being a bloody good metallurgist, he'd done all sorts of work. He was a BSc Metallurgy, or BSc Bachelor of Science, a Bachelor of Geology, the Boy Scouts leader, a ham radio designer and operator, the leading expert on allergies in Northern America for a while. And in his spare time, he decided to plot, measure, and lay out a large section of the now rather famous Appalachian Trail. It goes all the way from the Canadian border down to Florida, I think. So a tremendous bloke. But anyway, I digress. I learned a lot about manganese steel from Howard, and he was, and this is back in the late 60s mind, there was quite a lot of discussion about some of the new options with manganese steel to improve service life. And Howard said, well, they won't do it with plain manganese steel, and they won't do it with minor improvements. You remember that? And I said, oh, yeah, right. As the years have progressed, it's been, manganese steel was developed over 100 years ago. But nobody's come up with a better way of making a steel to do the jobs that manganese steel does, as well and at the same pricing level. Some of the later developments, yes, they might have marginal increases in service, but they cost a lot of money to implement. And that was what Howard was getting to. So that's manganese steel. You don't really want to deoxidize the last group of steels, the stainless steels. They're all different. They need to be treated differently. Remember, some of them have nitrogen added to them. So you don't want aluminium going anywhere near them. So I hope that wraps it up. The references, Hubbard, survey of the levels of nitrogen and hydrogen dissolved in steel. Very interesting paper. Lorigan Elsey, the occurrence of intergranular fracture in steels. Woodfine and Quarrel, of course, are the immediate successors to Lorigan Elsey. They further investigated the effect of aluminium and nitrogen on the occurrence of fracture in steel. Sidey, the effect of aluminium nitride. I might sound boring, but believe me, all of those papers were very, very interesting reading. And then we get on to Linden and Billington. The oxidation of steel with calcium, silicon, aluminium, magnesium, silicon alloys, and so it goes on from there. And that's why I say, don't worry about that stuff. Just stick with aluminium, calcium silicide for carbon low alloy steels. Strata, or CTI International, whatever they call themselves these days. Number 7, the deoxidation and inclusion formation in steel castings. Very, very informative, but boy, it'd bore you to death. And that's why you don't really need to. If you want to, go for it. And on the last subject, on manganese steel, Howard S. Avery's would have been about his last collaborator, Johnny Tasker, who was an ex-Strata, England metallurgist. Austenitic manganese steel, fact and fallacy, where he derides all of those who are trying to argue with over 100 years of development of manganese steel. I thank you very much for your attention. Oh, just the last thing, Appendix 1. I spoke earlier about knowing what the liquidus of your particular steel grade is. And it took me a while to figure out how to do it, but I eventually succeeded. And I drew up a program on Excel, a spreadsheet, and fitted all of those in. So now I know it can be done. So if you want to, there may well be one over the counter these days, I don't know. But the data is there and it's free, and make use of it. So thank you for your attention and good night. Any